So welcome everybody to today's seminar, and we have Umut Gursoy from Utrecht, who is going to tell us about some of his new work on hydrodynamics of spin currents. I'm sure all of you know, or you're familiar with Umut's works, and he has been one of the major players in applied ADS safety, and also in other things. And so over to Umut to tell us about this this new uncharted directions in hydrodynamics. Over to Umut then.
Okay, well, thank you very much for the invitation and the nice introduction. So this is well, first of all, let me start by saying that I hope everybody in the audience and the loved ones of the audience will be vaccinated soon, and there's not going to be serious health issues in the near future and later, because yeah, all the world is worried, of course. So this work in particular is going to be on spin currents. So that's there's some kind of new direction that we started together with my my PhD student, Domingo Gallegos, some time ago. And the first paper we have written on this was holography. So this is kind of a professional deformation, if you want. You want to explore some idea, and the first thing you do is holography. But instead, we should have been doing hydrodynamics first. And then we have done the hydrodynamic analysis together with Amos Yarom from Technion. And so most of this talk is going to be about the second paper, which appeared January this year. But if I have time, I'll also talk about the holographic approach. But this is going to be a hydrodynamics talk. It's not going to be applied holography. So, and please just interrupt me at any time if you have any questions. I'm happy to discuss the details. And so let's start with the motivation. So, well, the main motivation is, of course, the spin transport is playing a more and more prominent role in many different research directions. So, for example, in condensed matter physics, we are familiar with these new areas of research, spintronics and liquid spintronics, and that are becoming more and more interesting. And essentially, these are based on, these are strongly correlated materials, and the spin flows much better in the presence of strong correlation. So this is the kind of motto it's been used in these directions now. So this is quite it's a very interesting research direction. And so these things, the transport of spin degrees of freedom can be realized in many different systems as well, like graphene, Dirac and Weil semimetals, and other strongly correlated electronic systems, etc. But for us, for high energy physicists, I mean, I don't know the audience, maybe I'm assuming that we are mostly high energy physicists here. For me, at least, the main motivation comes from quark-gluon plasma. And because there is recently, it has been observed in the heavy ion collisions that spin transport is also playing some important role there. And then there's this ... of course, that spin degrees of freedom, the transport of spin degrees of freedom is also playing some important role, say in astrophysics, in neutron stars, in magnetars, even in neutron star mergers, where we describe the post-merger phase by evolution of hydrodynamics coupled to GR, and there the spin transport can also be playing some interesting role. So nobody knows yet, but so there's all these ... So this is a general interesting problem. So and the motivation, of course, my motivation is to construct a hydrodynamic description of spin transport in the relativistic regime. So in particular, the high energy motivation comes from this recent observation of spin transport in quark-gluon plasma. So let me explain in one slide what this is doing. Can you see my cursor?
Yes, Umut.
Okay, so here on this corner you see a scheme. It's a cartoon of heavy ion, an off-central heavy ion collision. So there is some initial. So this is an off-central collision, which means that there is some initial angular momentum, which is just transported to the total angular momentum of this quark-gluon plasma created after the collision. And so this quark-gluon, so this total angular momentum breaks up into small vortices. So this is a very vertical fluid. So it is actually, you can give it a number. So the amount of rotation per second is like 10 to the 22. Of course, these astronomical numbers we are familiar with in quark-Coulomb plasma. And what the observation is that, so these vortices essentially, because of the spin-orbit coupling in the system, so you can think of this, I can explain maybe on this corner much better. So this is the creation of the quark-Coulomb plasma after the collision. So this is the quark-Coulomb plasma, this thing in the middle, and there are different velocity gradients, as you can see, because of essentially the geometry of the collision. Right? So because of these velocity gradients, you are going to produce, so this is essentially another way to say that there is some total angular momentum in the system. And this angular momentum is going to break up into vortices. And this angular momentum, because of the spin-orbit coupling, is going to turn the spins of the individual particles, or if in the absence of a quasi-particle description, that it will produce some kind of a spin current in the system because of this spin-orbit coupling. And then this spins has been observed, actually. So the way they observed is that they observed the global polarization of a particle called hyperon. Okay, so this hyperon particle is a baryon that has spin 1/2, and it's spin. So the nice thing about the hyperon is that its decay, the main decay channels into a proton, and the proton that it emits, the momentum of the proton it emits in the rest frame of the hyperon particle is correlated with the spin of the original father hyperon. Okay. So that means essentially that you can infer from the protons that you observe at the end of the collision on your detector. You can detect their momenta, and you can reconstruct the amount of spin in the system, and you find some non-trivial result. Okay, so this was something recent in 2019. And that essentially stirred the community. People are quite interested about this. And there have been some works, of course, early works on this, theoretical works on this, but now this is confirmed. Okay. And another motivation, I'm still talking about motivation here, is these kind of experiments that condensed matter experiments that I mentioned. And I think there's one which is really worth explaining in a little bit of detail here. And this is more or less the same picture. So we're all familiar with what happens if you have a fluid that is flowing in a tube in the presence of a magnetic field. This is going to produce some electric voltage because of the Lorenz force. So the same kind of, the idea of this experiment was that they did the same kind of setup here. There is a fluid that is flowing in a tube in the presence of some vorticity. So they make some vorticity. So the way they produce vorticity is because of the friction at the wall. The velocity gradients are, so there's some non-trivial velocity gradient from towards the middle of the tube, and that essentially ends up making some vortices, small vortices. And here they've seen that these vortices produce some spin voltage. So that was, at least this was the aim. And they claim that they have seen this. This is a paper published in Nature. There have been no other experiments yet reproducing the results. So I would be cautious, but still the idea is clear how you would produce some kind of spin voltage. And what you, in the end of the game, what you see is that there's some spin density produced which is proportional to the vorticity, and there is some spin current proportional to the gradient of the vorticity.
So this can I ask something here?
Yes.
This is something that you're saying is simply empirical observation. So what my question is essentially that if there is no typically kind of Goldstone mode associated with spontaneous breaking of angular momentum, like of rotation symmetry, unlike, for example, the breaking of boost symmetry gives us this velocity vectors of velocity fields of hydrodynamics, but there is no such Goldstone mode associated with breaking of, say, rotation symmetry in a crystal.
You will see. That will be like there will be like spin chemical potentials, if you like.
I see, but
wait a second, and then you will see probably when I introduce so this is all motivation for the experiments, from the experiments, and now once I construct the theory, I will of course have to define the dynamical variables. And from the dynamical variables, you will see. I'm not going to use that language of spontaneous breaking of symmetries, but it should be equivalent in some sense.
Yeah, so this is a little bit confusing because usually we do not have such, like people have studied, I think, effective theories in different contexts, no? And
Yeah, I will come to effective theories.
You are going to come to that, yeah. But
of course.
So in this context, my question was whether the spin orbit coupling is essential to transfer this mechanical vorticity to something.
But this is motivation. These are just experiments.
Okay.
So like, I mean, for me, so all these experiments are assuming, so all these pictures these are just cartoons, assuming that there is some kind of quasi-particle description, right? So spin orbit coupling and etc. So what I will do is that I will assume that all of that quasi-particle description is, I will not assume that, and I will just construct the hydrodynamics in the language that you are more familiar with.
I see. But in this context, the spin orbit coupling is very essential in these experiments, at least to couple
there
the
should be
spin
something,
to the...
No, but yeah, indeed, but there should be something that I mean, if your question is what is sourcing the spin current, here it is vorticity. But I will come to, I will tell you that there is a generalization of this concept. Okay. What would be sourcing the spin current would be something like a spin chemical potential. So I will introduce this concept of spin chemical potential.
Okay.
And that will be essentially, I mean, that would of course be equivalent to vorticity or whatever in near term equilibrium, but it doesn't have to be in general. So I will generalize from this. Yeah. Wait a second.
Okay. Thanks. Okay.
Great. So thanks for the question. So these are So this tells me that I should move faster, probably. Okay. So, but the idea from all these experiments is that hydrodynamics should be used as a universal description, because in quark-gluon plasma we also know that hydrodynamic description is playing an important role. It agrees very well with the data, and so relativistic hydrodynamics in general can be used as a general prescription to understand the spin transport. So, and that's what we will do. And I will be using this modern version of hydrodynamics in terms of theory of slow variables. In general quantum field theory, you are all familiar with the fact that you can divide the system into fast variables and slow variables, and the fast variables are going to be relaxing to a perturbation. If you make a perturbation to the system from around some equilibrium value, they will be relaxing back to this in a very short time, tau relax, essentially because they are not conserved, so they can change their magnitudes in a given space-time point. But slow variables do not do that, because slow variables are conserved quantities. They cannot change in a given space-time point. They have to be transported from one point to the other. So this takes some time, and because of that, they are called slow variables. And if you, in any kind of system where you can, this kind of description is valid, you can write down an effective theory of conserved quantities, which is organized in derivative expansion in terms of these time derivatives and the gradients, space gradients. And this L is just the mean prepath, etc. So this is the kind of notion that we are all familiar with. So this is, if you like, the modern version of understanding of hydrodynamics as a theory of conserved quantities. So in this case, what we have is two basic operators we are talking about: energy momentum tensors. The stress tensor is always a part of the game. And on top of that, we want to understand transport of spin. So we introduce a spin current. So here, this upper index is essentially telling you the direction of the flow. So this is how the spin transport, the direction of spin transport. And these lower indices are just defining the direction of the spin. So this is, of course, relativistic generalization of the notion that we all know in just a flat space, where this is ij. For example, 1, 2 would correspond to some spin in direction 3, and perpendicular to that plane. So this just defines the plane of the spin. So the first, I would like to mention some early work on the subject. So this is, of course, a definition of hydrodynamics of spin is not this is not the first time that we are doing this. There have been some early work, but the important thing is that we will take a different approach, which is closer to what Ian was essentially hinting at. So that approach is going to be hydrodynamics in action formalism, and this is the formalism that has been, I mean, partially it was divided, it was all developed in India by Shiraz, Nabamita, Sayatani, and all the great people there, and together with another paper, Janssen and Amos Yarom, my collaborator, et al. It was all in 2012. I will be using this. So let me just recap the idea. The idea is to construct an effective action formalism for hydrodynamics. But I will just do this in the example of a charged fluid in the presence of external sources. So this is just to recap, right? So this, I'm not going to be using these formulas in the rest of the talk. So this is going to be just a recap. After that, I will come back to generalize this to spin. So suppose that we have a charged fluid in the presence of some external sources. So the external sources would be the metric and the vector field in this case. So you just write down the most general scalar, right? And as a function of these external sources, G and A. And you obtain the hydrodynamic equations by just from diffeomorphism and gauge invariance. So gauge invariance is going to give you this current conservation equation, and the diffeomorphism invariance is going to give you the conservation of or non-conservation of energy momentum tensor in the presence of some work done in the system. So, and then the next step is to define, so assume that there is some kind of thermal equilibrium in the system, so which means that there exists a killing vector, zeta. So this killing vector zeta is going to, from using this killing vector, you can define essentially the hydrodynamic variables in your system. So one of them is going to be the norm of this killing vector, that will be the inverse temperature. The killing vector itself normalized would give you the fluid velocity, and you can also define the electric chemical potential by dotting it with the external source A. And then from this, so this is going to be the total number of degrees of freedom, which are the dynamical variables, whose number match the number of equations you have in your system, and then the rest is going to be just writing down constitutive relations and solving the system. Okay, so that's the idea. And what we want to do now is, as I was alluding to, is to do the same thing for the case of spin hydrodynamics. So in the spin hydrodynamics, instead of the electric current, we have a spin current in the system, and the stress tensor is, of course, always has to be there. That's the marginal operator in every quantum field theory system, which is a part of the operator product algebra, both in the ultraviolet and in the infrared. So it's always there, and we can do this. So the idea is to run the same game, but instead of using these two external sources, I will be using field bind because that's more convenient. And instead of A, I will be using the spin connection, omega. Okay. So you are all familiar.
Are you putting a torsion here? Are you putting some torsion here?
Yeah, you're always like two pages ahead.
Okay, sir.
So yes. Then the question is that, however, okay, so you want to do, so this is perfect, so you can do this indeed. So because we all know that the spin connection indeed couples to, at least for a system of fermions, for example, it couples to spin current, etc. So it really is similar to is playing the similar role to this. But does this really make sense? How can we go and identify the transport of spin degrees of freedom free of ambiguities in the system? So because we know that there are ambiguities. Whenever you try to define a spin current in quantum field theory, there will always be ambiguities because that's a part of your total angular momentum in the system, which can be divided into an orbital part and a spin part. And the conservation laws of this total angular momentum and the stress tensor is essentially preserved by some transformation called the Belinfante-Rosenfeld transformation. Right? So this is just, you introduce some kind of three-index object, phi, which is antisymmetric in the last two indices, and the energy momentum tensor transforms with derivatives of that. Spin current can be transformed just linearly, and you can choose this phi to be exactly as to cancel it to zero. So we can set all the spin current to zero. So what are we talking about? The claim,
this
the
is
first
exactly
claim,
what I was going to ask you. So
yeah, exactly. So
yeah,
right. So
okay.
this is
So
the
you
answer.
can set the S to 0 then. You can completely set the S to 0 and
Exactly,
then
but no. Yeah,
J.
yeah.
Okay.
But the claim is that indeed what you need is torsion, right? So this kind, if you want the same kind of ambiguity exists even in the absence of spin, right? So you can define energy momentum transfer in different ways. But in hydrodynamics, we always, so the right way to do it is the right way to do to go about this problem in effective field theory is to assume that you have a small curvature. You put your system in a small curvature, so it should be extendable to this small coupling to small curvature, and that gives you a precise definition of the metric of the energy momentum transfer as the variable conjugate to the metric. So here the same thing is true. Essentially, what you need to do is that in the end of the game, you have to send torsion to 0, but you have to define the system at finite torsion and then send the torsion to 0 as a limit. So this removes the entire ambiguity. Okay, so that is the claim. And let me just substantiate this claim. So to see this, you can try to derive this Belinfante-Rosenfeld ambiguity in this language. So let's do this effective action language. So let's imagine that we have some quantum field in a non-trivial Lorenz representation with non-trivial spin, and then we integrate out all the canonical degrees of freedom to derive some generating function as a function of the external field bind and the spin connection. Right? Then we can define the energy momentum transfer and the spin current by just variations with respect to E and omega. Okay, so these are these two quantities. So far everything is fine. And then however, when you derive this, right? So when you make these definitions by making variations, so these variations are not really independent of each other in the absence of torsion because of this compatibility condition, right? So this dE, so the covariant derivative of the field bind with respect to the spin connection should be set to 0 in this absence of torsion. So this means that essentially these variations of E and variations of omega are related to each other. And by using this constraint in this variation, what you see is exactly the same form, the Belinfante-Rosenfeld form. Okay, so the kind of energy momentum transfer you obtain will be exactly of this form. This is precisely the ambiguity. However, this ambiguity is completely gone when you just relax this condition by defining on the right-hand side, introduce a torsion. So this TA, what you see here from this argument is that this TA, this torsion, is precisely the Belinfante-Rosenfeld ambiguity. So if you keep TA as an external source, you will remove the ambiguity completely, and in the end, you can send TA to 0, exactly like defining your theory on some non-trivial metric, and then sending metric to flat in the end of the game. So this removes a lot of ambiguities. Here, the same thing is true. Okay, so this is so what torsion is to the spin current is what metric is to the stress tensor, if you want.
So Umut, you are only putting torsion in the spatial, if you're, I don't know. So
no, you have to do it consistently. You have to put it everywhere.
So it's also one space, one time.
Of course,
okay.
Of course, yes.
And then what does that come out as?
Yeah, it will be precisely this spin chemical potentials, if you want. We will come to this.
Okay, thanks.
Yeah. Yeah, I will do that decomposition later. You will see. So you can do the decomposition, of course, by using this fluid velocity U, right? So that's the way of Lorenz covariant way of doing it. We will do that. So and it will be more practical for me to use the contortion rather than torsion. And I'm assuming that this notion of contortion and torsion are familiar with you. But if it is not, please ask me, whenever you want to ask, please stop me. So the contortion is essentially defined by using the spin connection. So the spin connection can be decomposed into two parts in the presence of some non-trivial geometry with a torsion. So this is the torsionless part, this is the torsion part. So this torsionless part is given in terms of the derivatives of the field bind. So in the limit where the field bind is flat, the metric is flat, this is gone. So, and the spin connection and the contortion becomes equivalent. And the contortion can be written in terms of T, as you know, by just anti-symmetrizing. So eventually, as I said, I will be sending contortion to 0 at the end of the game, because in quark-gluon plasma, there is no contortion. So here, this is just, if you like, this is a bookkeeping device to be able to derive this hydrodynamics. But in the end, we have to send this bookkeeping device to 0. You have to get rid of it, like a cutoff. But still, you will get some non-trivial spin currents. So this way of doing it, this particular way of precise way of doing it, is important, not to miss any terms in the constitutive relations, because there can be some terms that are order k, and there will be terms that are order k in this effective the generating function. And even if we send k to 0 in the end, after taking variation with respect to k to define the spin current, you will get some non-trivial spin current even in the limit k going to 0. So this is important. And finally, I want to mention some last thing about the torsion. That yes, in quark-Coulomb plasma or in quantum field theory in general of high energy physics or particle systems, the torsion doesn't really play any important role, and we can set it to 0. However, in condensed matter systems, it is used as some kind of some effective dynamical degree of freedom that captures the deformations in the system. So for example, dislocations in condensed matter systems, the dislocations in the atomic structure. So here, this example is from graphene. You can see there's some kind of distortion here. So these dislocations can be defined precisely in terms of torsion, because essentially how you define the dislocation. So this is exactly the same thing as taking two vectors. In this case, I'm just idealizing it by making it a square lattice instead of this hexagonic lattice. So suppose that you start with a square lattice, and you just parallel transport the two vectors that defines this square lattice with respect to the other, and the difference between the endpoints is given by this Burgers vector. And if this Burgers vector is non-trivial, it is proportional to the torsion in the system. It can be described as the torsion in the system. This is the definition of the torsion, right? So this in the continuum limit, when you go to the infrared regime of this theory, you are going to end up in the presence of dislocations. You are going to end up in some field of these Burgers vectors, or a field of torsions, if you want. So this hydrodynamic description of these kind of systems in the presence of dislocations are precisely what we will be deriving. But as I said, this is also important. This is also, I claim that it's the right thing to do also for the quark-Coulomb plasma, even in the absence of contortion. Okay, so I will now start the real talk. Any questions so far? Okay, let me go ahead. So what we want to do now is to use the same steps that I introduced before in the example of a charge current, and generalize it to the spin current. So in this case, the generating function is a function of the field bind and the spin connection. In the presence of torsion, we will keep torsion in the game, and we will derive the hydrodynamic equations by essentially symmetry principles, right? So the first thing that gives rise to the conservation of the stress tensor is the diffeomorphism symmetry. So if you make a diffeomorphism transformation of the sources of the external fields, they are given by these d derivatives. And this d derivative, and in the end, we want to demand that this effective action is invariant, and that will give one of the equations of motion. And the other equation of motion comes from the local Lorenz transformation. So in the local Lorenz transformations are of this form. So field bind transforms non-trivially. The spin connection is, of course, transforms precisely as the gauge field, because that is the gauge field of local Lorenz transformations. And this d is the covariant derivative, etc. So if you assume that these two the effective action is invariant under these transformations, you get these two equations. So the first one comes from the diffeomorphisms, the second one comes from the local Lorenz transformations. And you see that the first equation is precisely of the same form as the energy momentum tensor conservation or non-conservation in the presence of some external gauge field. And this analogous term is this one, right? So here, this is this field. So you should think of the Riemann curvature as the field strength of the spin connection, and the object that is conjugate to the spin connection, which is J that is conjugate to the A in that example, is going to be the spin current. So this is precisely of that form. And there's an additional term in the presence of contortion. So this is an antisymmetric part of the energy momentum tensor that couples to the contortion. So this can also be understood as some kind of electromagnetic, some kind of work term. So the second equation is coming from these local Lorenz transformations, and that gives the conservation of the spin current. Actually, it's not conserved in the presence of some antisymmetric part of the energy momentum tensor, as you can see, and also in contortion. Okay, so this, from here, we can see that if you want to generate, if you're if you're a spintronics person and if you want to come up with a system where you generate spin current non-trivially in an ideal system, let's say, you need an antisymmetric part of your energy momentum tensor and some contortion, for example. So this may be one way to do it. So these are just sources for the spin current. So these are the equations that we want to solve. So the next question is, what are the number of the hydrodynamic degrees of freedom in the system? So here I'm just rewriting these two equations. There are 4 equations here because this mu index is free. And here there are 6 equations because this S is antisymmetric in the mu nu indices. In total, there are 10 equations. So we need 10 hydrodynamic degrees of freedom. And they are exactly analogous to the charged fluid case. This will be one of them is going to be just the norm of the Killing vector, which is just defining the inverse temperature for you. And the Killing vector itself defines the fluid velocity. So there are 3 of those because u squared is 1. And you have mu AB. This is in total. So mu AB is the spin chemical potential. This is obtained by contracting the Killing vector with the spin connection. And because of this antisymmetry of the spin connection, these are 6 variables we have. So in total, we have 10 variables. So what we want to do is the next step, of course, it will be just to introduce the constitutive relations for T mu nu and S lambda mu nu in terms of these variables. We have to expand those in a derivative expansion. And then by just plugging back into these equations, it will give you the hydrodynamic phenomenological equations that you would like to solve.
So Umut, again probably a split question. So here, when you go back to flat space, then the spin chemical potential should all vanish, right?
We will see, yes, in the absence of sources.
In the absence of sources. Okay.
So in the hydrostatic equilibrium, you can still have some non-trivial spin connection. Okay, you will tell me what I will tell you. Okay. Yeah, this is a general rule by now, and you always you have to if you have a question, wait one slide, and then if I don't answer your question the next slide, then come back. Okay, it's a good thumb. Okay, great. So the bottom line of the slide is that these we should be defining these spin chemical potentials that are constructed out of these spin connections. So this is so far, of course, for a high energy experimentalist, this is all garbage, right? So we have to define how these things are defined in the experiment, etc., in the flat space, and I will come back to that in the end of that talk. But for us, for theorists, this is some quantity that makes sense. This is completely analogous to the electric chemical potential. Okay. So, well, as you can guess already, the amount of complexity will increase exponentially as we go on in the higher derivative expansion, because there are many more degrees of freedom. We have to also consider contortion, etc. So there can be many different tensor structures you can come up with, and you have to include all of them in the constitutive relations to be for consistency. So in this talk, I will make a simplification, and I will assume that the spin current will be of order 1 derivative. So its order in derivatives will be 1. So this tells me that the antisymmetric part of the energy momentum, the stress tensor, should be order 2 in derivatives. And it also tells me that this contortion should be of order 1. So this is an assumption. I could have been taking this as order 0. And probably in this condensed matter systems, this example I gave in the dislocations of the graphene, that would be the wise thing to do. But this is something that you have to keep in mind. So this is what I'm assuming. And now let's go for let's derive the constitutive relations slowly. So let's first think of hydrostatic equilibrium. So let's have this system in mind and then assume that there is some kind of thermal equilibrium in the presence of time-independent sources. That means essentially that these external fields, this external field bind in the system and the spin connection should be invariant under time translations, right? So the derivatives of these equations under the Killing vector with respect to the Killing vector should be 0. And from these two conditions, you can derive the following equations. So this is kind of an answer to your question, Maya. So the first thing that you may be familiar with in the absence of spin is, for example, that an equation that relates acceleration to the thermal gradient. Right? So you can always have some acceleration in your systems. If you think of some atmospheric pressure, the temperature goes down as you go far away from Earth, and so there's this temperature gradient is precisely balanced by the acceleration that is given by the the gravitational force. So here that would be something like that is it's always the case, right? So this comes from just this equation. And from this one, you get a new equation. So this new equation looks exactly like this. So this is the thing in the box is the new thing. So here, what you get is that if you define your spin chemical potentials like this, you see that in the hydrostatic equilibrium, the equilibrium in the presence of sources is in that limit, the spin connection is related to torsion and acceleration and vorticity. So acceleration, vorticity. Those are the quantities that do not vanish. But for example, the shear part, sigma AB, or the expansion theta, the del of U, those vanish in the equilibrium, the hydrostatic equilibrium. But these quantities do not vanish, and they are related. They become related to the spin connection. Sorry, the spin chemical potential. So these together can be also written in terms of what is called the thermal vorticity in the system. So in the absence of torsion, what we see is that what we defined as spin chemical potential is precisely what experimentalists understand as thermal vorticity. Okay. So this hydrostatic limit essentially allows you to understand what quantities we are talking about. But formally speaking, mu AB are just independent variables out of equilibrium as well. So those are the kind of quantities that we would like to solve, and they should approach to this what is called the thermal vorticity in the limit of hydrostatic equilibrium. So we also see.
Umut, again, a short question. Maybe not that answer is not in the next slide, but yeah. So so you do not need a spin orbit coupling, right? In here to turn on.
Well, here I mean,
it's a very general.
Spin orbit coupling. I mean, there's some quantity that to be able to define a spin orbit coupling, you need to use a microscopic definition. So I don't hear this is hydrodynamics. There's no microscopic definition here.
Exactly. So
the spin orbit coupling. So what I'm saying is that, as you will see, when I write down an effective action, the effective action will be given as so the first term in the effective action will be some pressure term, and that pressure will be written in terms of these spin chemical potentials, right? So that's the most general thing that you need to write down. And the way that I'm going to write down the most general thing, so there will be some spin susceptibilities. So these spin susceptibilities, when they are non-vanishing, they will be precisely equivalent to the spin orbit coupling.
Yeah, but this statement so far didn't even need an action. It's simply a kinematic statement. There's the fact that
no, this exactly, that's right. So here this is just a kinematic statement, right? Yeah.
So and it implies that if you have a vorticity in hydrostatic equilibrium can have vorticity. There's a vorticity, there has to be a spin chemical potential.
Yes, that's right. That's right.
So that means that you do not need any spin orbit coupling to turn on this spin chemical potential.
No, the spin chemical potential can be there, but it doesn't mean that the spin chemical potential will result in a spin current. Oh, so this is, you see.
Okay.
So what I was referring to was that the next step is going to be calculating the wave of the spin current, and the wave of the spin current is going to be given in terms of this, but there will be terms that those coefficients may be zero. So those coefficients will determine.
Okay, I see.
Yeah.
Okay, thanks.
Again, just wait one slide. So right. So thanks for the question. This is all very good. So so from here you see also two other things that one thing that I mentioned already, and I want to stress this because all these early works on spin hydrodynamics in the context of quark-gluon plasma, etc., were really using this quantity thermal vorticity. And maybe one little extension we did in this paper with Amos and Domingo was to extend this notion of thermal vorticity into something bigger that we call spin potential, which becomes the same thing in the limit of in the thermal equilibrium in the absence of torsion. But from consistency purposes, I think it makes more sense to think of this spin chemical potentials. And another thing that you see is that if you want to, again, from a practical point of view, if you want to produce some spin density in your system, perhaps a good way to do it is to think of some thermal vorticity, like in the case of quark-gluon plasma, or torsion, like in the case of dislocations in the condensed matter. Okay, so how are we going to determine this mu AB then? So for that, we need to construct the hydrodynamic. We already have the hydrodynamic equations, but we need to introduce the constitutive relations and substitute them in the hydrodynamic equations to obtain equations of motion for mu AB. So, and the way to do this in this modern language of hydrodynamic action by using the action principle, what we had to do is essentially just to write down the most general action, constructed the most general scalar constructed out of this temperature, velocity field, field bind, and contortion, and their derivatives. So for that, let me decompose the spin connection into two parts. The first part is the contraction of this omega AB with a mu index down with this velocity field u mu, and that will give exactly this. That was the definition of the spin potential. So this is the spin potential part, and then there's a so this is the time-like piece, and then there's a spatial part, the spatial torsion. So this is what Ayhan was saying. So this spatial torsion would be completely analogous to those dislocations in the atomic structure I mentioned. In the end, I will be setting them to 0, but this will be playing a more important role. So that will be the spin potential. And another thing that you should be doing that to simplify the analysis is you take this mu AB, the spin potential. So let's ignore the spatial torsion for the moment. Let's focus on this spin potential. You take the spin potential and you can decompose it further into two vectors. Essentially, because you have at your disposal another vector, the fluid velocity UA. So this will be completely analogous to defining the electric and the magnetic field starting from a field strength, if you want. So these are exactly the same equations. So this will be like some electric, if you want, in quote unquote, spin potential and some magnetic spin potential. And the next thing that you would like to write down is the hydrodynamic action. So the most general hydrodynamic action is some general scalar that is constructed out of temperature and the scalars that you can make out of these two vectors. Okay, so those vectors are just m square, little m square, and tilde square, and their product, m times m tilde. Okay. So this will be the ideal fluid pressure. So this will be the ideal term. And then on top of that, of course, you have to write down all the gradient corrections that are given in terms of some derivative expansion of these variables. And here I'm going to put the spatial torsion also in this case, in the second term. Okay, so that's essentially answering to your question, Ayhan. This the spin orbit coupling is somehow that information is contained in this pressure term in your action. So far, it looks like I haven't done anything, but in fact, we have been doing a lot of things just by writing down this equation here. Because from this, let's focus on the ideal spin fluid now. Just from the fact that you can write down some pressure of this form, constructed out of these spin potentials and the temperature, you can derive the constitutive relations by taking variations with respect to the field bind and the spin connection. So if you take the variation with respect to field bind, you will obtain the stress tensor. The stress tensor will be of this form. So these two terms are completely familiar to all of us, the energy density and the pressure density. But there's a new term that comes from this dependence of P on the spin chemical potentials, m square and the big M square. So with this big M square, I'm defining it here as the Poincare dual of the little m vector. And similarly, m tilde AB is just the Poincare dual of this the other m. So this is kind of there is this new term. So this new term you can understand as some kind of, so these are the spin susceptibilities that I was talking about, and this new term is of the form of a spin pointing vector. So this is precisely as the E cross B kind of term, and you can see that the only non-trivial component of this is the momentum component. It only contributes to the momentum. So this kind gives rise to some kind of momentum term that is completely arising from the spin potentials. So this is the way to understand it, I think. This is how I understand. And then you can go ahead. So from this construction, you also get these Gibbs-Duhem type relations. For example, the energy density is given in terms of pressure and temperature like this. So there is an additional term here. There is the spin density, rho AB. So this is another equation that you get, the spin density times u lambda. So this is the form of the spin current. And the spin density can be expanded in terms of spin chemical potentials precisely like this. So there is this formula, this Gibbs-Duhem relation that relates the spin density as the variations to the spin susceptibilities and the spin chemical potentials. Okay, so this is the ideal spin fluid. Okay, so to answer your question, well, you can also ask the question: what is the where is the spin orbit coupling? The spin orbit coupling is precisely in these terms. If these spin susceptibilities do not vanish, then it means that spin chemical potential produces some spin density in your system.
Thank you.
Okay, so then the next thing that we would like to do is to go beyond this, right? So we want to go and we can still, the first thing that you typically do is you first do the ideal spin fluid, and then you still want to stay within the realm of hydrostatics, but go one order in higher in derivatives. So that's what I would like to do, completely analogous to this charged fluid, electrically charged fluid. But again, in this case, it is very complicated, because now with all these different variables at hand, you can write down many different, you can construct many different terms of order 50 or so. And to keep things simple, what we have done in this paper with Amos and Domingo was to assume while invariance. So we assumed the conformal and parity invariance of the fluid. So we were just looking at the conformally invariant and parity invariant fluid. That's not typically the case for a quark-gluon plasma. Okay, but let's make this approximation. And the way to implement this conformal invariance and parity invariance is, well, parity invariance is clear. You just look at the parity invariant terms in your effective action. The conformal invariance is that you demand while invariance of your effective action. And so this while invariance is going to, if you make the while transformation of the external sources, and if you have while invariance of your theory, then essentially that means that the fluid that couples to this is going to be conformal. And from this argument, you make a while transformation of this form, and you demand that your effective action is invariant. And what you get is a conformal word identity in the presence of spin. So this may also be something not familiar to everyone, that typically what we get is just T mu mu equals 0. But in the presence of a spin current, you get instead T mu mu equals the gradient of S. So this ring gradient is the torsionless gradient. Okay, so this is how we define. So this is this is an equation that I will be demanding. And the first thing that you see is that, first of all, among out of these little m and capital M, only one of them survives, because the other one is not conformally invariant. So this capital M becomes conformally invariant, the little m is not. This means that essentially your energy, pressure, and spin density can be expanded only in this quantity. And also from conformality, you see that, for example, that you would get the first term would be of the proportion of T to 4, and the spin density should be T squared together with this MAV term. So this is the kind of expansion that you get, and there will be, of course, higher derivative corrections. Okay, so this is a conformal fluid, the energy, pressure, and the spin density of a conformal fluid. Then the next thing is to write down the most general correction, again, for a conformally and parity invariant fluid, in the presence of torsion. So those will be, so the most general term that you can write down in the first derivative, I mean, this first order in derivatives, in the first order in contortion is going to be in this term. So there are three different terms that you can construct. I'm not gonna get into details of this because it will become, as I said, very quickly, it will be complicated. So this kappa K and Ka, kappa A and K are constructed out of this torsion by taking various contractions with the U and the projection tensor delta mu nu, etc. I'm not going to get into that detail. But what you have to do is that you have to define these three different coefficients, chi1, chi1,2, and chi2,2. And there will be a correction. Again, I'm not showing the analogous equation for the energy momentum tensor. I'm only showing the spin current because the other one is very complicated. You see that in addition to the ideal piece, you get these three little pieces. So for example, if you want to look at this term, so these are all proportional to the spin chemical potential. In the absence of spin chemical potential, they would vanish. But here, this doesn't. It looks like a universal unsourced component because it all depends if chi1 is 0 or not. This is some coefficient, some transport coefficient that we don't know how to calculate unless you have a microscopic theory. But you can imagine that there is a microscopic theory where this is non-trivial, and that would produce some kind of non-trivial spin current.
Sorry, Umut, what is this capital delta?
Capital delta is just, sorry, I forgot to mention, that's just a projection.
The projection is orthogonal to you.
Yes. Okay, thanks for asking. So then we want to do more, right? So this is all you can do. Of course, you can go further ahead in the derivative expansion, etc., and write down all the equilibrium, the hydrostatic terms that you can construct. But you can also do more, and you can do non-equilibrium physics, and that is really the essence of the hydrodynamics, right? So you really want to go far from equilibrium. And there are a lot of indications, even in small size systems and also in quark-gluon plasma, that the hydrodynamics start applying really even you are far from thermal equilibrium. Right? So that's some notion that we are all familiar with. So it may be quite interesting to apply this this construction to quark-gluon plasma and try to see if some kind of hyperon polarization would be generated at the early stages of the collision. So that would be completely non-equilibrium. For that, we should really go beyond the hydrostatic equilibrium construction, and we should give up this. So the action gave us all we can, all it can. Those are the hydrostatic equilibrium terms. And then to go beyond this, you need to construct by hand the non-equilibrium corrections to the energy momentum tensor and to the spin current. So here I'm showing down all the possible terms that you can write down, the non-equilibrium terms. So these are all the terms, all the conformally invariant and parity invariant contributions to the spin current that vanish at equilibrium. So for example, at equilibrium, the equation that we had for equilibrium is this. So if you use this decomposition of mu AB in this equation, you are going to get you will see two type of equations, and those equations will be exactly those, that this and that vanish when you expand this mu AB in terms of capital M and little m, the way I did. So you will get these two equations. So here, that's why I'm using those two combinations which vanish at equilibrium to construct a non-equilibrium correction. So these will be just those 5 terms that you can write down. And they all come with different transport coefficients that I'm denoting sigma I. And the first one is proportional to the, it comes together with this shear tensor. And this is some kind of an interesting term, so that you see that shear, so this will give rise to some kind of a shear-induced spin current. Okay, so this is something may have some interesting applications, I don't know. But then if you want to constrain these transport coefficients, the only tool that we have in this analysis is both Onsager relations and also production of non-trivial. So the positivity of the entropy current. So starting from this this object that we have to define some entropy current, and I will come back to this entropy current discussion later. We have to demand that the gradient of the entropy current, divergence of the entropy current, is positive definite. If there are terms on the right-hand side which involve some of these combinations of these transport coefficients, which is not manifestly positive definite, then we have to set those combinations to 0. This is the usual game. So I will come back to that later. Okay, but for the moment, I just want to flash for a second the kind of equations that you obtain from this analysis. Now I'm including all these pieces. So this correction that is non-equilibrium correction, this correction that comes from this first order hydrostatics, and the ideal piece. If you take all of those and write the full constitutive relation and substitute that in the hydrodynamic equations that we derived earlier, then you get those kind of, these are the equations that you obtain. So for example, this is and these derivatives, I'm not even defining those derivatives, some kind of derivatives, covariant derivatives if you want, that contain the contortion, etc. And so, but you see that this is the kind of phenomenological equations that I had in mind. So for spin, to determine what spin chemical potentials are, we have to be solving these equations. So spin chemical potential is some dynamical variable that reduces to thermal vorticity in equilibrium, but in general, it's some kind of an object that you don't know, you have to solve for it. And this is the way to solve. Okay, so what we need is initial conditions and these transport coefficients to be able to solve this. Okay, so So this concludes the theoretical part of the talk. Let's see. So now I'm almost done. If you give me like maybe 5 minutes or 10 minutes, I can maybe just finish the applications.
Oh, sure, Umut, please. Yeah.
Okay, thank you. So I hope that I will be done in 5 minutes. So the now we want to apply this to heavy ion collisions. So this is a picture that I just I'm flashing it again. So this is right after the heavy ion collision. You have these spectator ions that are flying away from the collision region, and they leave this debris of the quark-gluon plasma. And general lore in these applications of spin hydrodynamics to heavy ion collisions have always been that you have some kind of non-trivial gradient of the velocities, and they will give rise to some thermal vorticity. And because of spin orbit coupling, somehow this thermal vorticity turns into polarizations of these heavy ions that are coming out of this quark-gluon plasma. Like, sorry, not the heavy ions, sorry, the hyperon part, the hadrons that come out, and those are like some hyperons, etc. Now, this is true. This is almost true, but the claim that so what we see from this construction is that this is true only at hydrostatic equilibrium. Because we have seen that indeed you are going to derive polarization, which is exactly the same thing as the spin density or spin current in general, from these spin chemical potentials. And spin chemical potentials are not the same thing as thermal vorticity, but they become the same thing at equilibrium. But in general, if you assume that the system is not necessarily at hydrostatic equilibrium, you will get corrections to that. So how does the calculation goes? So you define the polarization of an identified particle, like this hyperon particle, etc., from this formula. So this is just a Pauli-Lubansky vector. Right? So this is a contraction of momentum with the spin, essentially, and the spin written in terms of the spin potential. So this is a formula that you can derive by using kinetic theory, or you can write down just from quantum field theory. This is correct. And then here, let me explain what it is. So these are the momenta of these particles. I'm assuming that these particles that are coming out of this quark-gluon plasma, like these hyperon particles, are massive. So there's some mass term. In the massless case, you also have the Pauli-Lubansky vector that analogous to massless particles, but that's a different thing. I will be always assuming massive vectors. And you integrate over the freeze-out surface. So freeze-out is essentially where this quark-gluon plasma, this plasma hadronizes and turns into hadrons. So you integrate over that freeze-out surface, and you introduce some kind of Boltzmann type distribution for the particles that are coming out. And this X is the location on the freeze-out surface. It also depends on their momenta, and there's some normalization factor. And this mu, the spin potential, is entering it precisely here. So in all the earlier works, essentially what has been done was, instead of spin potential, people were writing these phenomenological equations which only involve the thermal vorticity. So here we propose to write down the full equation with the spin chemical potential, and the spin chemical potentials should be obtained by solving these equations. So let me do that. Let's do that now. So let's simplify again the problem further by assuming some kind of Bjorken flow. So we want to construct a Bjorken flow in the presence of spin current. So Bjorken flow is a nearly, so it comes from the nearly flat rapidity distribution of the particles produced in the heavy ion collisions, and that means essentially, from a practical point of view, mathematically, it just means that all these dynamical hydrodynamic variables you have in your system should be independent of the rapidity eta. And the full symmetry of the Bjorken flow is just this boost invariance times the translational, the transverse translations, and this Z2 flip in the rapidity direction. Okay, so and by just the symmetry, essentially, you can immediately solve the hydrodynamic equations, and you get that the only non-trivial component of the vector of the fluid velocity is u tau, which is 1 by normalization. And the temperature can be obtained as a function of tau. You see that there is this shear correction, There is this ideal piece that goes like 1 over tau to 1/3, etc. And if you assume that there is no, so if these initial conditions, if the symmetry is not broken, then you get no spin polarization. The spin polarization is 0, just by the symmetry, essentially. You cannot write down some non-trivial spin chemical potential in respecting these symmetries. So what you have to do is that you have to reproduce these initial conditions in your system. So you have to deform the Bjorken flow in such a way that you are going to get some non-trivial correction to the velocity in the rapidity direction, in the z direction, which is given essentially by this momentum in the q direction, in the x direction. Okay, so that should be proportional to that. And this b little b is just the impact parameter. So in the case when the impact parameter goes to 0, you are not going to get this situation. Okay, so these initial conditions essentially already break this Bjorken flow. So what we have to be looking at is some Bjorken flow with some perturbation. So this is the perturbation itself. So then what I'm going to do in the next slide is to write down the hydrodynamic equations for this perturbation and solve them to calculate this polarization tensor. And this is the result. So I'm not going to get into details. I will just mention one thing, that you have to assume, I mean, it's a good assumption that you can assume that the hydrodynamics solution respects this limit where the kinematic viscosity in your system, which is defined by this quantity divided by time, is much smaller than 1. Within that assumption, you can obtain actually analytic results. So for these two objects that you can construct, this little m and capital M, and those they decay in time as some power law with some exponentially suppressed piece. And if you, from these two, if you just now go ahead and just plug them in this equation to calculate the polarization of the average polarization of the hyperon particle, then you see that it just matches the experiment well enough. But of course, what we have done in this matching is that we matched one of the points, right? So because these are proportional. The proportional constants depend on the transport coefficients and the initial conditions, which we don't know how to fix. So those overall proportional to constant, we just fit it by this data point or something, and then the rest is just prediction, which agrees relatively well. Okay, so this is essentially, I'm not claiming that this is what is going on in the quark-gluon plasma, because we have been making a lot of assumptions in the last 3 slides or so, but this is just as a proof of concept. This is already good enough to explain certain things. So, and then you can go ahead with this construction and come up with more realistic hydrodynamic descriptions, and then make good predictions, hopefully. So the last thing I want to, so let me just see if there are any questions about this application.
Yeah, just one thing I get puzzled by this. Typically, if you look into chemical potentials, you would expect they will simply have power law like decay. But here on top of the power law, you have some exponential piece.
Yeah, that comes from this shear term. Yeah. Let me see. I mean, this is exactly what you get. Yeah, this is exactly what you get. I mean, I don't think that I have a good insight into that. So these shear pieces, like this term, for example, if you solve the system consistently, then indeed you get those exponential suppressions. I don't really have a good explanation of what.
Yeah, because normally if you think that if it is something like a slow mode, it will have only a power law like relaxation, not an exponential relaxation, right? So this is
no, but this is not slow mode, right? So there's a momentum here. So there is a non-trivial momentum that I'm assuming. So this is not.
Oh yeah, okay. Now that explains.
Okay, so that is the thing. So there is an exponential of IQ.
There's a QX. Okay,
right,
okay.
right.
No. Okay,
exactly.
okay.
Yeah.
Okay, thanks. Okay.
So exactly. So you don't have those terms in the absence of momentum.
Okay. Yeah, indeed. If your Q goes to 0, then this exponential piece also goes.
Exactly.
Okay. Thanks. Thank you.
Okay, so one last slide on the entropy current. So for those of you who are familiar with this, this the entire the modern hydrodynamics, how we construct entropy current out of it, etc. It's a very important and essential problem to address this. So the question is whether the entropy current that you can write out of these hydrodynamic variables is positive definite or not. So the entropy production is positive definite or not. So for the ideal fluid, the entropy current that you can write down is this. This is just the entropy S times U mu. And there you can see that this vanishes precisely. Okay, so the gradient is vanishing. But then we want to go one order beyond ideal, and the next order in the derivative expansion, you can write down essentially two different terms, the canonical term and the non-canonical term. Non-canonical term and the canonical term, again, assuming that there is a conformal and parity invariant fluid, this is the most general object that you can construct. So the non-canonical term is given by this, the acceleration, the expansion, del of U, and then this spin chemical potential M. But the canonical piece is also given by S times U mu, the ideal piece, together with these corrections that vanish in the ideal limit. Right? So this is the most general.
Sorry, why does capital M not appear in the entropy current?
I'm assuming again conformally invariance.
Ah, okay, sorry, yeah.
So in that case, unfortunately, the only thing that you get is that you just determine these coefficients in the non-canonical contribution to the entropy current in terms of these transport coefficients that I introduced, which entered the effective action, this chi1. Nothing depends on chi1,2, chi2,2, but you get only one condition, that this the shear coefficient, the shear viscosity should be positive definite. But this is kind of unfortunate and disappointing that, of course it should be, and this is what you get. So to get something more non-trivial, some on these spin transport coefficients, the sigma I that I showed, for example, sigma 1, sigma 2, etc. You have to go one order beyond, and that's complicated, and we didn't do that.
Umut, one thing. So here, is it clear that you are only relaxing to hydrostatic equilibrium, right? That's the solution you get. That mu AP is equal to, or there is other possibilities.
There are other possibilities. No, there are other possibilities. It doesn't have to be relaxing to thermal equilibrium. I mean, I am assuming, of course, like to be able to construct the action, I'm assuming that we do a derivative expansion, but I guess from the action, from a general, as a general solution to these hydrodynamic equations, you may be able to get some non-trivial, non-relaxing solutions as well.
Yeah, but that is sort of unusual, right? Because normally in usual hydrodynamics, at least if you trunk it up to first order, you will go to just a usual hydrostatic equilibrium.
And, but there are these hydrodynamic attractors.
Yeah, but that occurs at much higher order derivatives.
Yeah, but here the same can happen, right? So you can
yeah.
So the only right. So you generalize these hydrodynamic attractors, also including by now these the spin chemical potentials as dynamical degrees of freedom, and there will be associated quasi-normal modes, etc., and those can be summed up, and the same story can go through. It's just that it's much.
Okay. I know I had a much more down to a kind of trivial question. So I was asking on the right-hand side of greater than equal to 0. So you typically find things like sigma square plus stuff, right? And if you put sigma square to because of positive definite thing, you have to put sigma to 0. And so if you put all those conditions on the right-hand side to 0.
This is what it is, right? So it's just giving you that. Because in this case, we only have sigma squared. This is a conformal fluid. There is no bulk viscosity. There is not much. So you only have the shear viscosity, essentially. And from the reason that you don't get for the spin transport coefficients anything is because I'm assuming that they are first order in derivative to start with. So to be able to get some non-trivial conditions on them, you have to go beyond in the derivative expansion, one order beyond this in the entropy current.
Yeah, but my question was whether you get this hydrostatic because we did a similar computation for superfluid hydrodynamics, and we saw that this so-called Josephson condition comes out automatically by requiring this greater than equal this right-hand side to vanish. So then then it doesn't always give you some, it gives you sometimes a condition also for that you actually relax to the right equilibrium. So for example, whether you would be able to get mu AB is equal to minus omega V is equal to the spin chemical potential has to be equal to the thermal vorticity minus of that from here.
You mean assuming that there is no dissipation? Is that,
assuming, yeah, I mean, no, yeah. When
equality,
yeah, when dissipations, yeah. To have it as an equality, you also require that.
No, I don't think so. Yeah, it's more complicated in this case because you can still have torsion-like terms. So if your question is whether you would be able to get that equation of hydrostatic equilibrium that relates the spin chemical potentials to this vorticity directly from the entropy current, then I think the answer is not that quick. No, because of this these torsion terms that you have to also think about. If you set the torsion to 0, I think yes.
Okay.
Yeah. Okay.
Okay.
Good
Thanks.
question.
I'll look into it. Look into your work.
Okay. So, well, yeah, we have a PRL style paper, so you're not going to get more than this talk, I think. So it's like all these short explanations, but a longer paper is coming up. So I'm not going to get into holography because there's not much time. I just wanted to mention maybe just in one slide that it's an extremely interesting question to ask how you would so how would fluid gravity correspondence, for example, work in this case. So for that, I think, and the main question would be to be able to write down, to calculate the Kubo formulas, first of all, to write down Kubo formulas for this Neve transport coefficients, spin transport coefficients, and to calculate them in maybe a first order formulation of fluid gravity correspondence using this, then extending this spin connection and torsion towards the bulk in the presence of some black hole and all of that. And so this work has been done to some extent in our earlier paper with my student Gallegos, but only in a very specific context where we can write down analytic black hole solutions, and that was like 5-dimensional Chern-Simons gravity. So in that case, you get some non-trivial flow with you can calculate everything precisely. It's dual to a conformal fluid, but it's very specific. So and the more general construction has not been done yet. Okay. So I will skip all of that. So this is the Chern-Simons low log gravity, and then you get some non-trivial results, etc. But I'm going to skip this because this is not the most general thing. So let me summarize. Well, we have done some systematic study of spin transport in relativistic hydrodynamics, and derived hydrodynamic equations and constitutive relations up to second order in the derivative expansion. And the first thing that I mentioned in the talk was that the torsion is playing a major role in this entire construction as a bookkeeping device, but it's an important one. It really tells you how to take in which direction you should be taking this torsionless limit. And then another maybe key message is that you have to introduce these Neve dynamical variables, the spin chemical potentials, and they are the basic dynamical variables of your system, valid also out of equilibrium. In equilibrium, they reduce to the quantities that we know, vorticity and thermal gradients, etc. But out of equilibrium, they have their own life, which should be determined by solving these hydrodynamic equations. And then, I mean, even though I didn't really mention, I didn't explain in detail, one nice thing about holographic calculations is that it really helps you identify some novel transport channels, and it also computes the associated conductivities for you. So if you have more time later on, I can mention this after finishing the official talk. So, well, thank you very much. So let me just end by the outlook. The one thing that is left to do is to calculate the entropy current in more detail, and in higher order in derivatives, and get some constraints on the transport coefficients. Another thing is that can we do this, do some weakly coupled quantum field theory analysis and get some universality in the, try to see if there's some kind of universality in the transport coefficients by matching to the hydrodynamic calculation. What I have in mind is something analogous to chiral magnetic conductivities and things like that, which can have some analog spin conductivities as well. And there is a mismatch that I didn't mention, but there is a mismatch between theory and experiment of in the spin hydrodynamics business that is essentially coming from the longitudinal polarization of the hyperon particles, so some more detailed quantity on this on a plane perpendicular to the longitudinal polarization of these tensors. You see that there are some different signs that these theories predict. So there is a sign mismatch. We haven't done this calculation in our setup, so this setup is completely new. The spin hydrodynamic setup is new, and this may be able to solve this sign mismatch if we were able to calculate the spin transport coefficient. So that's important to do first. And yeah, and then of course, like matching to holography, kinetic theory, etc., is an interesting thing to do. And well, in general, so let me end with the general note whether there will be some observable effects of this novel spin transport. For example, in condensed matter systems where dislocations are playing an important role is also quite an interesting question. So thank you very much for your attention.
Thanks, Umut, for this really fantastic talk. It was super interesting. And let's have some questions now.
Thank you. I hope others also.
Yeah. No, certainly. I would like to also introduce, after we finish the recording, Alex, Sukrut, and Toshalis, who are working with me. But let's first finish this recording. So I have a very small remark actually about going back to the slide where you had this exponential decay. So I think the exponential decay is simply coming because there is no, this one, this exponential decay with Q square is simply probably, I think, is coming because of the fact that there is no zero mode or something like a sound shear mode that is related, that omega and Q can go to zero together. So I think this is how this could be the reason why you have this exponential.
Right. Yeah. Yeah, that's a good comment. Yeah, so if you had a gapless mode, indeed, yeah, I guess that's right. Yes.
Yeah, and I have a small question as well. So you mentioned as an application, heavy ion collisions. I was wondering if spin hydrodynamics would also be relevant for neutron star mergers.
Oh yeah, so that was I was trying to mention it in the first slide, and it may be right. That's a good question. That's a very good question. So there are two stages of the BNS, the binary neutron stars. So the first phase is before merger. So in the pre-merger, so there have been some early work dating back. I don't really have the names on top of my head, but dating back to like maybe 2-3 years ago, people were talking about vortices inside the neutron stars. So even before the merger, right? So they can play some interesting role if you assume that the core of the neutron star is made of quark-gluon plasma. And it's plausible that because of this, high rotation, there will be some vortices in this core, and those vortices may be affecting the equation of state of the plasma. So that may be this is a question separate from the mergers. And for the mergers, I don't really know. So that's a practical question in some sense. So that should really be answered by some expert running these hydrodynamic simulations for the binary neutron star mergers. And I would really doubt that the spin of the ejecta would be really affecting the evolution of the post-merger binary neutron star system. But it may be important for other things. Like, I mean, it really depends. I think it's a very good question, but I don't know how to how to quantify this. So the answer is, like, it's, of course it's open, but I think for example, I mean, for the magnetic field, so you can ask the same question for magnetic fields. So neutron stars also come up with, you know, they have very large magnetic fields. So you can ask the question whether these magnetic fields are going to influence somehow the signal, like the gravitational wave signal. Or but for the gravitational wave signal, it doesn't. It's very small. You wouldn't be able to see it. But there's an electromagnetic counterpart. This electromagnetic counterpart, this kilonova, the magnetic fields and conductivity of the system, etc., it will be sensitive to that, I think. So in this case, also, there you have to define the judicious, like, really variables, observables, which would be very sensitive to vorticity in this sense. So I'm sure there is vorticity, but I don't know how the gravitational wave signals would be sensitive to that. I don't think that it will be, but there may be some other observables that you may construct. I don't know.
Okay, thanks. Yeah, very interesting.
Okay, Umut, thanks. Let us now end the official talk.
Okay.
Okay, so I'm stopping the recording.